For centuries, humanity has looked to the heavens with wonder. Autonomous Sky Tracking and Recon Apparatus, or Astra, hopes to make celestial viewing and education easily accessible to teachers and students. At its core, Astra is a self-contained, portable system designed to autonomously point, identify, and track celestial and orbital objects. Whether capturing images of planets or the sun, Astra produces high-quality imagery with minimal user interaction. Astra faces several major challenges. We created a custom graphical user interface, or GUI, that can show a live camera view with camera controls while also calculating where the telescope is pointed and moving the telescope to a desired location based on user input. Additionally, we had to create a way for students to be able to see images from a camera while also getting hands-on experience looking through a telescope. Along with precise mechanical movement and a portable power system, Astra has many unique elements that make it a challenging yet exciting project. The impact on education and outreach is substantial. Designed for middle schoolers and high school users, Astra serves as an intuitive gateway in engineering and astronomy. Its user-friendly interface, combined with an onboard library of celestial information, transform the system into an engaging, interactive tool for community events and educational demonstrations. Combined with a website to help students learn about optics and astronomy, Astra is an ideal tool to help students get hands-on experience looking into the heavens. In a premier stargazing location like Tucson, Astra becomes more than a telescope. It becomes a platform for inspiration. By engaging local high school students with the broader community, it fosters curiosity and interest in optics, engineering, and space science.
One of the main engineering challenges with the optical system was deciding the best way to approach designing a system that enables the user to look through an eyepiece as well as take an image. We initially considered using a faux eyepiece and microdisplay to mimic the feel of looking directly through a telescope, though the user would be viewing a digital reconstruction rather than actual light from the stars. We created several prototypes and conducted trade studies on the best possible sensor to purchase, as this would be the main optical component. We then discussed our plan with local astronomers, professors, and mentors, and decided that this approach would be somewhat deceitful and could be disappointing for students when they realize that they are not seeing actual light from the stars, but rather a reconstruction on the screen. Because of this, we explored other options and finally settled on a flip mirror design that replicates a DSLR camera. This allows us to display a live camera view to our touchscreen display or allow users to look through an eyepiece at the stars.
The Astra power bank must sustain 48 hours of active use under System Requirement 4.4.3, while every module stays under 35 pounds per Requirement 4.5.1. Our initial design used individual lithium-ion cells per subassembly, each compliant with IEC 62133, with Thermal Requirement 4.2.1, an operating range of 41 to 110 degrees Fahrenheit, as well as voltage sag under operation, introduced swelling and power risks that ruled out approach out. We migrated to a Dr. Prepare 100 amp hour lithium iron phosphate group 31 battery. LFP chemistry offers superior thermal stability, minimal voltage sag, and greater energy density per dollar, while staying compliant with IEC 62619 for stationary storage applications. Power conversion using the DIN-mounted regulators per EN 60715. Overcurrent protection is handled by a Blue Sea fuse block, providing per-device fusing to SAE J1284 blade fuse standards. The grounding architecture follows a single-point star topology per ABYC E11. Verification was performed using a TI INA 260 current sensor spliced in series on each XT60 supply line. Data was logged over serial, exported to CSV, and analyzed in Python, validating current draw, voltage stability, and runtime margin against our 48-hour requirement. With this system, we met all weight, thermal safety, reliable conversion, and verified power delivery challenges successfully.
The mechanical system for Astra acts as the foundation for the entire telescope and tracking setup. It supports the optics mounting structure and enables controlled rotation while maintaining stability in an outdoor environment. Our main goal was to create a rigid and stable platform that could support the system weight and allow for precise rotation for polar alignment. We also wanted the design to be modular, easy to assemble, and practical to manufacture. In order to achieve this goal, we combined commercial off-the-shelf components like the dioptron mount with our custom-made tripod assembly that our team designed and built. We focused on load distribution using reinforced materials for strength and lighter materials where possible to reduce overall weight. We also incorporated friction-reducing elements like ball bearings, to improve rotational performance.
To design and build the mechanical system for the Astra project, we first explored different approaches for motorizing the right ascension and declination axis to achieve accurate celestial tracking and automated targeting. From this research, we considered the ioptron hybrid strain wave mount as an example of a high-precision tracking system. Furthermore, we enhanced our design by incorporating automated azimuth and declination control. In addition, the mechanical system was developed using the ASME Y14.5 geometric tolerancing practices and ISO shaft fit specifications to ensure accurate torque transmission, minimal backlash, and reliable astronomical tracking. The biggest challenge we faced was balancing stability and precise rotation while under load conditions. Adding stiffness and contact can increase friction, which creates unwanted stress on our gear system. However, reducing friction to improve gear motion can lead to unstable and uneven load support. Our initial mechanical tests highlighted these trade-offs, showing that achieving both at the same time is not straightforward.
One of the main software issues encountered was deciding the most effective way to interface with the COTS hardware used for the telescope tracking and the imaging system. We had to write our own code to control these two components, which came with a variety of issues, with the most prominent one being timing issues. Because our GUI supports both direct port and Wi-Fi communication with the mount, we designed our code in a way that feels seamless with low latency performance that ensures signal integrity when sending multiple commands. Similarly, while the camera functions could capture frames, the tasks of managing thread synchronization with our GUI without causing crashing was left completely up to us. Beyond technical execution, the Astra project is deeply rooted in educational outreach. Consequently, we designed the GUI to be highly accessible, featuring an intuitive layout and simplified controls that allow the students and amateur astronomers to engage with professional-grade hardware without a steep learning curve.
We need to run tests in order to ensure that our system meets every requirement. Alexis, what tests are we running now?
Right now, we're pointing at a star, and we're testing if our mount can counteract the Earth's rotation.
This means that the star will appear stationary to the camera and telescope, so we can take long exposure images and see deep space objects. Astra provides students with an opportunity to get hands-on experience looking into the heavens. The sky isn't the limit anymore, it's just the beginning.